Good morning, everyone. Before we get back into just kind of jump right in from the aerobic or oxidative glycolysis talk, I just want to make sure we're all on the same page before moving into this thing, because I think sometimes students can get caught up in these different systems, and they get if you get a little unclear about one, that can bleed into another, and I just want to make sure we're all on the same page. So you might remember that in the beginning of our series of lectures, in the beginning when I first introduced metabolism to you, we talked about these different systems. So you have the phosphagen, the ATP-PCR system, you have anaerobic, also called fast glycolysis, and then you have the oxidative system. And I showed you these different graphs and the colors and lines. Okay, so we talked about the ATP-PCR system. That was the very, very brief system where you have phosphocreatine, creatine kinase comes in, breaks that up into phosphate and creatine, and then boom, that phosphate goes attaches right to an ADP, creating ATP. So that's a 1-to-1 ratio, right? That system. For every one phosphocreatine creates one ATP. It's really short and fast, right? That's why we use that during our very, very high intensity experiences. Okay, whatever that may be. It could be exercise related or survival related, whatever it may be. And that one again lasts about 3 to 15 seconds. The next system that we talked about was anaerobic or fast glycolysis. Remember, that is when we start with glucose or glycogen and it goes all the way through the system and it eventually gets converted into lactate or lactic acid. Okay, so that is going to be our primary energy mechanism it can be our primary energy mechanism from anywhere from 30 seconds to 3 minutes. It really just depends on your level of fitness. Okay, so those are the two systems we introduced originally. Now we've gotten into the oxidative systems. And the first one that we've been talking about that we just covered in the last talk was carbohydrate oxidation, right? That's also called aerobic glycolysis or slow glycolysis. Just want to make sure everyone's on the same page. So instead of starting with glucose and glycogen and ending at lactic acid, well, now we have a sufficient amount of oxygen available, right? It's called oxidative. Therefore, it's going to go from glycolysis and then into the Krebs cycle, and then everything we made from glycolysis in the Krebs cycle is going to go into the electron transport chain, so we can get all of the energy from those high energy carrying compounds we talked about, like NADH and FADH, and we can get a bunch of ATP from it. Now, what I also want to remind you of, now that you're really starting to learn more about these systems, is don't forget, in the beginning of the semester, I showed you these graphs. Okay, this one is the rate of ATP generation. You guys can see that the phosphocreatine system is really, really quick. However, its capacity, very, very low, right? Doesn't last very long. Glycolysis, and this is specifically talking about anaerobic or fast glycolysis. This one's not as fast as PCR, but it's definitely faster than aerobic glycolysis or carbohydrate oxidation. Same thing. However, you look here, that doesn't last really, really long as well. It lasts longer than they show in this graph. I think when I drew it, I drew an addition onto it, but you get the idea, okay? And now we're in carbohydrate oxidation. It's a lot slower, and I think you can understand why, right? Not only does it have to go through glycolysis, but it also has to go through the Krebs cycle, and it also has to go through the electron transport chain. Okay, so it has to take extra steps. However, when you look at, when we look at its capacity, well, it's a lot higher, right? Because last time we met, I asked you to do an accounting of all of the ATP that we get from one glucose molecule, and I hope you were able to see that the amount of ATP we get from aerobic glycolysis is a lot higher, about 10 times higher, than the amount of ATP we get from anaerobic glycolysis. But again, it has to go through a lot more steps, which takes more time, which means we have to be working at a lower intensity in order to utilize that. And we haven't gotten into fat oxidation yet. That's going to come next time. All right, so again, just kind of hoping that you guys have a good feel for this. If you feel like you don't truly understand it, you have to reach out to me. I'm begging you, okay? This is it can be kind of complex to really understand it. But if you have any curiosity questions, post them in the discussion boards that I have weekly. Send me an email, set up a virtual meeting, whatever it is. I want you guys to be able to understand this just as well as I understand it. Because once you do, then you can really get a good grasp on everything in a lot of your exercise science classes, because it gives you a better understanding of, okay, exactly which system are we working, and how do I create a training program to improve this system, or what exercises are going to be best for an athlete that utilizes this system, or how am I going to best prescribe someone a diet, if you're a dietitian, to better equip these specific systems to allow this person to get through their ADLs or activities of daily living, right? Whatever it may be. This is going to certainly help you get a better grasp on that. So please reach out. I hope that you guys, I'm getting quite a bit of silence. I don't get a whole lot of emails from you, so I hope that's a good thing. That means you understand it well, but if not, please reach out. I'm begging you. All right, let's move into the new information for today's lecture. Okay, last time we spoke, we really got into the details of aerobic or oxidative glycolysis, right? So the three stages of that are, you have glycolysis, which, remember, that happens in the cytosol of the cell. And if we start with one glucose molecule, that nets us a total of 2 ATP in that stage, and 2 pyruvate and 2 NADH. So we get that ATP there. The NADH will go to the electron transport chain, and those 2 pyruvate will move through the PDH complex. Then we're getting into the Krebs cycle. So the Krebs cycle happens actually in the mitochondria, because that's where the PDH complex was, right? That was the gate. So those 2 pyruvate that we had will each turn into acetyl-CoA. So that gives us 2 acetyl-CoA. When those acetyl-CoA go through the Krebs cycle, remember, each time they go through Krebs, we get 3 NADH, 1 FADH, and 1 ATP. But because we have 2 acetyl-CoA, that would give us 6 NADH, 2 FADH, and 2 ATP. All of those NADHs and FADHs that we created in Krebs will also go through to the electron transport chain, right? Remember, NADH and FADH are high energy carrying compounds. The mere presence of them alone does not give us ATP, but when we take them to the electron transport chain and break them down, then we get a lot of ATP from them. Okay, so when we talked last time, I asked you to give me an accounting of where we get all that ATP from. Let's work on that together and see how close your math was to what it really is. When you watched the previous lecture, I asked you to do an accounting of how many ATP we get from one glucose molecule. Hopefully you did that, okay? If not, you should have. I would have rather you done that before you listen to this than during or after. But this will help you really understand just what I mean when I say, just when a system takes longer to get through all of its processes, it does have a much higher capacity. So what I want you to do is kind of listen to this, make sure you understand and remember where we get these from, because you'll need to know this for the exam, wink wink. But let's go ahead and look at this, okay? So this green shaded box here that you see is glycolysis, okay? So that's explaining to us what's happening during glycolysis. And just like we talked about, okay, if we start with glucose, we net 2 ATP, all right? So that is 2 ATP that they show here. That's where this level goes, so substrate level phosphorylation, all right? And we also get 2 NADHs. Well, those NADHs, as shown here, will go to the electron transport chain, okay? If you have 2 NADHs, and each of those NADHs give us 2.5 ATP, well, that's how we get 5 there, okay? So at this point, we have 7 total ATP. Well, In glycolysis, we also get to pyruvate. Well, those pyruvate will have to go through the PDH complex, and when they do, that gives us another 2 NADHs. Okay, so 2 times 2.5 will give us another 5. So we had 7 before we got there, add 5 ATP onto that, and that gives us 12. Okay? Then those pyruvate, that once they go through the PDH complex, they get converted into acetyl-CoA. Okay, so if we had 2 pyruvate, that gives us 2 acetyl-CoA. Each of those acetyl-CoA are going to go through the Krebs cycle once. So if we have 2 turns of Krebs, that gives us 6 NADHs. You take 6 times 2.5 per NADH. That gives you 15 ATP. All right? You add 15 onto the 12 that we just had previously, so now we're at 27, okay? Also with those 2 turns, we're going to get 2 FADHs, okay? Remember, each FADH gives us 1.5 ATP per FADH, so that's another 3 ATP, okay? So now we're at 30, and also those 2 turns of Krebs gives us 2 ATP. Okay, so we add 2 ATP onto that 30. Now we're at a total energy yield of 32 ATP. Okay, now remember, if we start with glucose or glycogen, the only difference is 1 ATP, right? If we start with glycogen, it's already in the muscle cell. So if we were to do a total accounting for glycogen, that would give us 33 ATP, opposed to glucose, which would just give us 32 ATP, which is why our body prefers glycogen over glucose, because it goes through the same processes, but we yield more ATP from it. I hope that makes sense. This is definitely something you're going to want to remember. If I were you, I wouldn't remember, I wouldn't try to mentally take a mental image of this slide. If you simply remember how many ATP we get from each NADH and FADH, and then what we get from each stage, that's it. You can pretty much answer any question from that point. There's no sense in burning more energy trying to memorize things than you need to. Okay, so let me know if you have any questions on this. Remember, guys, which of these metabolic systems our body uses at any given point of time is going to be dependent on the intensity at which we are moving. Okay, we'll just say exercising to make it kind of easier for everyone to understand. If you're working at a very, very high intensity, that is going to force your body to shift systems. If you're working at a low intensity, also going to be utilizing a specific system. Okay. Now remember, in the last lecture I told you that our body uses the presence of oxygen in order to know which system it's going to use. And I've created a kind of a flowable diagram that I hope helps explain that with everything here. So before I kind of walk you through this, I just want to set the stage. Okay. So we have glucose moving to pyruvate, so that should tell you that this is glycolysis, this part here. Then those pyruvate go through the PDH complex, which is shown here with this little green line. Okay. Also, everything's happening here in the cytoplasm, and everything out here is in the mitochondria. Just to make sure you understand it, even though it looks different. Okay, I created this myself, so it's not going to look as pretty as something from the book. Then those pyruvate, after they go through the PDH complex, will be converted into acetyl-CoA. Those acetyl-CoA will go through the Krebs cycle. Remember, once citrate mixes, once acetyl-CoA mixes with oxaloacetate, making citrate, that will start the Krebs cycle. And then from each turn of Krebs, we get 3 NADH and 1 FADH. And then all of those will go through the electron transport chain, which is shown here. As long as we have oxygen present, that allows everything to work properly, oxidatively, to break glucose or glycogen down for the process of slow or aerobic or oxidative glycolysis. Okay, and it's the mixing of those hydrogens and oxygens that give us water. Okay, so hopefully you have a good understanding of what we're looking at here. All right, well now what I want to do is show you what happens in this system if we go from working at a lower intensity to all of a sudden working at a higher intensity. So I want you to imagine, you decided to start doing intervals, okay, sprint intervals. Well, you start with just a walk, and all of a sudden, in that walk, you've got plenty of oxygen available. The demand isn't so high that you're not meeting it, so you've got plenty of oxygen available. Now let's say you start to sprint as hard as you can. Well, what's going to happen to your availability of oxygen? Oxygen is still going to be available. Sorry guys, I got my windows open, it's loud outside. Oxygen is still going to be available. However, your supply is not going to meet the demand, okay? Because demand is very, very, very high. So what's going to happen is all of a sudden, notice if you look down here at the slide, all of a sudden we don't have a sufficient amount of oxygen available, okay? Well, once we don't have a sufficient amount of oxygen available, that is going to force the electron transport chain to shut down. Once the electron transport chain shuts down, then we're going to have an accumulation of NADHs and FADHs because they have nowhere to go. Once we have an accumulation of NADHs and FADHs, that is going to cause the Krebs cycle to shut down. Okay? Remember guys, I talked about negative feedback loops. Everything that happens at the end of the system is going to dictate what happens throughout and at the beginning of the system. This is what I mean by negative feedback. Okay? Well, once the Krebs cycle shuts down, then what's going to happen to acetyl-CoA? It's going to have nowhere to go, so it's going to accumulate. All right? Once acetyl-CoA accumulates, that is going to signal the PDH complex to inactivate or shut down. Okay? Well, once the PDH complex shuts down, pyruvate has nowhere to go, right? Remember, pyruvate only has one of two fates. It is either going to be pushed through the PDH complex and get into the Krebs cycle of the mitochondria, or it is going to be converted into lactate and eventually lactic acid. Okay, so if the PDH complex is shut, we have nowhere to go. Okay, so what's going to happen to pyruvate? It's going to be converted into lactic acid, and at this point, right, we're really our body has shifted from primarily being oxidative or aerobic. And because we started to do our high-intensity sprint, we didn't get enough oxygen. Now our body is shifted to anaerobic measures in order to get energy. Okay? So remember, it's going to be able to help us get ATP much faster. However, as a byproduct of that much faster production of ATP, we're going to be producing lactic acid. That lactic acid is going to create what's called metabolic acidosis. And that is when you really get that burning sensation that you do when you exercise. That's your body's way of telling you to slow down. Okay, I'm starting to become fatigued. If you continue to go on, you're going to start causing cellular damage. So that lactic acid is really seen as a signaling mechanism to tell you that you need to slow down because you're going to start causing more damage. Okay, it's very similar if you've ever broken a bone or sprained an ankle or something. And that is, it's sore, it hurts. That's your brain's way of telling you that that has to be immobile so it can heal, right? Your body has all these really interesting ways of helping you to tell you what you should be doing to keep you alive and keep you in a state of survival. All right. So I hope that makes sense. I hope this whole thing kind of helped you through it. You know, now you can imagine. So let's say that you stopped that sprint. And, you know, all of a sudden, those things start to go back to normal. So now all of a sudden, you know, let's say that we have sufficient oxygen available all of a sudden. Well, that's going to allow the electron transport chain to shut down. So all of our NADHs and FADHs are going to have somewhere to go. Once they have somewhere to go, that'll signal the Krebs to turn on. Once Krebs turns on, we get those acetyl-CoAs to move through. The PDH complex opens up, and then the pyruvate continues, and then we're constantly going through this period, you know, shifting from a full sprint, which might look like this, to resting, which is going to look more like this, to that back to that sprint again. So I hope that helps explain how our body shifts from one metabolic system, or primarily using one metabolic system over the other. Okay, so I know that I've taught you these different systems, these energy systems, kind of in silos, right, individually on their own. However, it's very, very important that you understand that it's not just one system, or the other, okay? It's actually all systems working together all the time. The only caveat to that is some systems are going to be doing a lot of work compared to others. And I put this table in here. This actually isn't from your ex-phys book. It's from the NSCA's Strength and Conditioning book. But it really helps you to understand that, okay, it's not just a light switch, right? Everything's kind of working on a continuum. So go ahead, take a look at this table with me. What this is showing us is someone's energy use, or where they're getting their energy from during a maximal cycle ergometry test. Okay, so if you're on a bike and you're working as hard as you can against the resistance, this is going to show us which system is putting in the primary contribution at different points in time. All right, so kind of follow along with me. So I want to look at this first column. Okay, this is showing us what's happening in the first 5 seconds of that maximal effort cycle ergometry, okay, when the person is pedaling on a bike. Well, their exercise intensity, percentage of max power output is at 100%, right? They're feeling, they've got a ton of energy, so they're 100% putting everything they can into it, everything they have available. Well, during those first 5 seconds, our anaerobic mechanisms, like ATP-PCR and anaerobic glycolysis, are going to be doing 96% of the work. Okay, they're going to be producing 96% of our energy. Notice that I didn't say 100% of our energy, right? It's 96% because our aerobic mechanisms are putting in 4%. Very small amount, but they're still putting in a little bit of work there. Okay. Now, what I want you to do is look at the time mark right here at 30 seconds. Okay, so we're 30 seconds in. This person is gassed, right? They're starting to hurt pretty bad. It's very, very difficult for them. Their maximum intensity or percentage of maximum power output is now at 55%. It's been cut almost in half because they're very, very tired. They can't produce as much power. All right. Now, look at the percentage of our anaerobic mechanisms. They've gone down to 75%. Because of the reasons we talked about, right? ATP-PCR doesn't last for very long, and our anaerobic or fast glycolysis is producing a lot of lactic acid, right? So they're feeling very, very fatigued, which has forced them to slow down a little bit. So now their anaerobic mechanisms are doing 75%, and aerobic has picked up that slack and is doing 25% of the work. Right? They've slowed down a little bit, which has allowed them to get a little bit more oxygen into their cells that they need. So our aerobic mechanisms can help do some of the work as well. Right? Remember, guys, even though I talk about this in a single muscle cell, this is happening throughout the entire body in every muscle. Okay, so everything is always working together to help us achieve that 100% of energy. All right, so we're getting all the energy that we can. That we can possibly get. So all systems are working together all the time. Now when we look at that person at the 1 minute or 60-second mark, now, they're really gassed. Their energy max, their power output's now at 35%, so it's dropped down substantially. And now they're working at 50-50, okay? So they're 50% anaerobic mechanisms producing the energy and 50% aerobic. And then that continues to go on and on and on. All right, until, it looks like at 90 seconds that person's still trying, but they're not getting very far. And then at 150 seconds and 200 seconds, they've stopped altogether, right? They could not continue that. So you can see, I hope this helps explain how these different mechanisms between anaerobic and aerobic are always working together in order to help us sustain life and achieve a consistent production of energy. Okay, let me know if you have any questions on this. Okay, so this is a question that I always ask class, and then I give them like 5 minutes to discuss. But because we are doing this online, I want to just kind of pose it to you here. This is actually a question that a classmate of mine when I was an undergrad asked, and I've always thought that it was a really great question because it really forced me to think, yeah, that's true. What the hell's going on here? So if our aerobic metabolism essentially gives us a limitless supply of ATP for energy, okay, why do marathon runners often hit the wall around mile 20? Okay, so when we say aerobic metabolism, that includes carbohydrates, which we've talked about, fats, which we have not talked about yet, and protein, which we will not be really talking about because I've discussed this at the beginning. We really shouldn't be using very much protein for energy unless we're in very high survival situations, right? We're using very little protein for energy, for ATP production, so we don't really spend a lot of time on it. But carbohydrates and fat, we do. All right. So if those essentially give us a limitless supply, why is it that a marathon runner will really hit that wall around mile 20? And if you've ever seen someone do this, they will can literally fall because they're not able to produce that ATP, right? And that typically very often happens around mile 20. Well, when we talk about this in class, people will say, it's because they don't have a sufficient amount of oxygen anymore, is typically the most common answer, because they run out of oxygen. And that's not true at all. Okay, we have plenty of oxygen available. We always have a consistent amount of oxygen in the air. It's about 21%, just under. It's 20.93%, if I remember correctly. That's how much oxygen is in the air that we breathe, and that doesn't go anywhere, right? However, what happens around that mile 20 mark for the average individual is that's the point at which we run out of glycogen. Okay? Remember, guys, our muscles store glycogen. They can store quite a bit of it. And if you continuously use that, your body is going to want to continuously use that for a long period of time. However, around that mile 20 marker for marathon runners, that's when those glycogen stores have been completely depleted. Well, what's that going to force them to do? Okay, that's going to force them to all of a sudden primarily rely on glucose, right, which is a big reason why a lot of marathon runners will, during their race, they'll take little things that have sugar or glucose in them to help continue to make sure they have a sufficient amount of blood sugar, so that will help them get through that point, and maybe even start to store a little bit more glycogen or refilling that fuel tank, if you will. Also, what's happening at around mile 20, so because their body is forced to use other molecules outside of glycogen, now they have to use fat as their primary fuel source. And fat is holy cow, it really is damn near limitless as long as you have any. However, when we talk about fat oxidation, get into that next time, you guys are going to see how fat oxidation takes way longer. It takes so many more steps than carbohydrate oxidation. Even though we get a lot of ATP from that, it takes a lot longer, which means we need a lot of oxygen available, which means we have to be working at a very, very low intensity, which is why someone will go from running to all of a sudden lying flat on the ground and not moving at all, or barely moving, or going to, being forced to walk or crawl in some instances. Okay, so just an application question that I hope made you kind of think, turn on a light bulb, like, holy cow, I never knew that. I thought it was interesting when I was an undergrad, and I hope you did too. All right, class, now it is time for you to take your quiz. So study, make sure you understand the material well. When you do study for my class, especially this one, it's much better to study from a perspective of understanding as opposed to a perspective of memorization. I remember myself as a student, I took a lot of classes, especially anatomy and physiology, where I really focused on memorizing. Memorize, right? And what that did was it really beefed up my short-term memory, but when it came to retention, I didn't really retain as much as I would have liked. However, in classes that, students really focus on understanding, like in EXSC, if you understand it well, you'll notice that this class bleeds into a lot of other fields and a lot of other subject areas. So if you can really understand the material well, that will help you retain the information, store it in your long-term memory. That way you'll get a lot more out of this class. So that's what I really test for. When you read my exams and quizzes, I really want to make sure that you truly understand the content. You're not just simply memorizing details, because that can become exhausting. The more you understand it, when you study from a place of understanding, the much better off you'll be in the long run. Okay? So if you feel like you don't understand something, it's your responsibility to contact me as soon as possible, and I will do my best to get in touch with you, hopefully we can set up a meeting or something like that before you take your quiz and your exams and so on and so forth. It's always best to do that as soon as possible, though. So without further ado, good luck, study smart, and let me know if you have any questions at all. Have a wonderful day.